Yes. Okay. So first talk of the session is apparently a very good paper. It's in fact the best paper, and it will be presented by Martin.
All right. So thanks for the introduction. I'm presenting joint work with Malte Helmert, Yusra Al-Khazraji, and Robert Mattmüller. And in this paper, we have investigated the relative pruning power of two pruning techniques that are both based on so-called partial order reduction. And that's it. Pardon? That's a good idea. It boots. Yeah. All right. So okay. So let's first have a look at the idea of partial order reduction. So what is partial order reduction about? So partial order reduction is an approach to tackle the state explosion problem that has been originally introduced in the areas of model checking and computer-aided verification roughly 20 years ago. And the basic idea of partial order reduction is to avoid an unnecessary blow-up of the state space that is induced by independent operators. So for example, let's consider this simple truck example. Say two trucks have to drive independently from a starting location to a destination location. And, well, I mean, it's kind of obvious that if only reaching the goal state is of importance, then the order in which the trucks drive to their destination location is not of importance. And, well, what we could do, or what partial order reduction, roughly speaking, would do is to commit to one of these orderings, which would implicitly cut one of these intermediate states of this diamond-shaped state space on the right. And, well, very roughly speaking, this is the idea of partial order reduction, and these are the settings where partial order reductions come into play. All right, so the current situation is that, well, as I've said, partial order reduction has been originally proposed in model checking and computer-aided verification, but already roughly 20 years ago. And, well, recently, partial order reduction techniques have also become quite popular in the area of AI planning. And various techniques based on this idea have been proposed, but in many cases, the formal relationships of these techniques, well, have not really been clear. And in particular, the relative pruning power of these techniques have been unclear. And one recent result in the setting is that the so-called expansion core method that has been proposed in 2009 for planning is actually a special case, an instantiation of a generic method called strong stubborn sets that has been proposed by Valmarie in 1989. And, well, this is an interesting result because it shows that expansion core actually is or belongs to this strong stubborn sets family, which is not obvious, but this result doesn't tell us anything about the relative pruning power or the pruning power of expansion core and stubborn sets. And well, this is actually what this work is about. So in this work, our goal was to improve our understanding of, well, the relationships of these techniques. And in particular, we have investigated the relative pruning power of these techniques. We did that on a theoretical level, but also on an empirical level within a fast downward planner and on IPC problems. So I will come back to this point at the end of the talk. All right, so before going into more technical details, let me first very briefly give the overall, well, preliminaries for this work. So we consider standard SAS plus planning, where we've given a finite set of variables to describe the state of the world. We have given operators that consist of preconditions and effects. And, well, I think you know all that. So we have given an initial state and a partial state that describes the goal states. And the objective is to find a sequence of actions that leads from the initial state to one of the goal states. And our objective, in fact, is to find a cheapest sequence of actions. Sorry? Okay. Okay, so now we can step in. So in the following, I will introduce on a high level strong stubborn sets and expansion core, and will afterwards speak about the relative pruning power of these techniques. So about our main result. So let's start with the strong stubborn sets. Aha, okay. So strong stubborn sets. So what is the general idea? So as I've said, strong stubborn sets is a pruning technique. And well, the idea is to compute in all encountered states during the search, to compute a subset of the applicable operators, and then only apply this subset of applicable operators, and in this sense prune the other operators. And the strong stubborn sets do this in a way that well, that optimality and completeness is preserved, because for every plan that is pruned, it is guaranteed that the permutation of this plan is not pruned. And doing so, well, the size of the reachable state space is potentially reduced. And the question is how to do that. So to introduce strong stubborn sets in more detail, I need two more definitions. The first definition is the definition of so-called necessary enabling sets. So I suggest to first give the formal definition and then to discuss it on a simple example to make it hopefully a bit more clear. So what are necessary enabling sets about? So for a state S and an operator O that is not applicable in the state S, a set of operators is called a necessary enabling set. If for all plans that start in S and include the operator O that is not applicable in S, it must hold that one operator from this necessary enabling set is applied before the first application of O. So let's have a look at this example, at this figure. Let's suppose we are in a state S, and let's suppose that we have two sequences of actions that lead from S to a goal state, the blue one and the green one, that also include O. Then, well, both sequences of actions must hit this necessary enabling set before the first application of O. And while having this definition, we have two rather immediate observations. The first observation is that necessary enabling sets are not uniquely determined. This is just because, well, once we have a necessary enabling set, we can always add more operators to the set and still preserve this property. And actually, this will lead to a, well, design choice for the computation of strong stubborn sets. I will come back to this later on. And the second, also a rather interesting observation, is the close relationships to disjunctive action landmarks. In fact, disjunctive action landmarks are a special case of necessary enabling set for a planning instance where the goal state is replaced by the precondition of O. So in a way, it's a disjunctive action landmark to reach the precondition of O. And that's also, again, it's interesting because disjunctive action landmarks, well, we've heard yesterday the history of landmarks, and disjunctive action landmarks are a rather recent concept. And the necessary enabling sets, well, have been proposed roughly 20 years ago. Now, the second definition, well, is a definition about operator interference, also a very important concept of partial order reduction. I think most of you know this definition. We say that two operators, O and O prime, interfere if one of these three conditions hold. So O and O prime interfere if O and O prime have conflicting effects. So if O and O prime write to a common state variable but with a different value, or if O disables O prime, or vice versa. So if O prime disables O. And then we have the observation that, well, if O and O prime are applicable in a state and non-interfering, then we can apply these operators in both possible orderings and, well, leading to the same state in both cases. So we can compute them in this case. And now with these two definitions, I can now talk about what are strong stubborn sets. So as I've said, they have been proposed in 1989 by Weherle. And well, strong stubborn sets impose constraints on sets, and all operator sets that satisfy these constraints are called strong stubborn sets. Now let's go through the definition, and then let's have a look at this example afterwards. So a set of operators Ts is a strong stubborn set in the state S. So if, first of all, Ts, this set contains a disjunctive action landmark, and then for all operators that are applicable in S and are contained in the set, all operators that interfere with this operator must also be contained in the set. And the third condition says for all operators that are not applicable in S, a necessary enabling set for this operator must be contained in the set. Now, let's have a look at this example, simple truck example, a little bit extended from the beginning. So again, two trucks have to drive from a starting location to a destination location. And in this example, we observed that the set, the drive operators, let's say, drive from A0 to A1 and drive from A1 to A2 is a strong stubborn set in the initial state. And why is that the case? Well, first of all, the set must contain a disjunctive action landmark. Well, the drive operator that drives from A1 to A2 certainly satisfies this condition because every plan must eventually execute this operator. This operator is not applicable in the initial state, so we have to include a necessary enabling set, which is the operator drive from A0 to A1. And in this case, we are done because, well, we would have to include all interfering operators with this drive from A0 to A1 operator, but there are no interfering operators. So we've reached a fixed point, and, well, now we can apply just all applicable operators from the set, which is drive from A0 to A1, and we can prune the other operator that is applicable that drives from B0 to B1. Okay, so much to strong stubborn sets. Now to the second technique that we considered, it's expansion core. Okay, so, well, to introduce this technique, well, I have to give two more definitions. I'm sorry for that. Expansion core, well, crucially relies on the notions of potential preconditions and potential dependence. And well, I suggest to just give the definition and then to have a look at an example afterwards again. So variable v is a potential precondition of variable w in the state S if there is an operator such that this operator reads the variable v, it modifies the variable w, and the precondition of O considering the variable v is consistent with the current value of v in the current state. And similarly, potential dependence. So variable v is potentially dependent of variable w. If there exists an operator such that the operator reads, in this case reads the variable w, modifies the variable v, and again the precondition of v must be consistent with the current value of v in the current state. So at this point I should mention that in the original work of expansion core there are some further optimization criteria that can be checked syntactically. These are rather orthogonal optimizations that can be applied to both expansion core and strong stubborn sets. We did this in the paper, but for simplicity I left this out for the presentation. Okay, now the expansion core method computes in every state a so-called potential dependency graph, which is a graph where the vertices consist of the variables, and we have an edge between two variables, v and w, if v is a potential precondition of w, or if v is a potential dependent of w, or there is an operator that writes both v and w. So in a way this can be considered as a state-dependent causal graph. And finally, expansion core, what does it do? So first of all, to prune, first of all it selects a goal variable that is not, well, such that the current value of this goal variable is not yet the goal value, the required value. And then, starting from this variable, it computes a so-called dependency closure of this variable in the potential dependency graph, which is a variable set that contains this variable and all variables that can be reached in this graph starting from v. And finally, well, EC of S is then defined as a set of operators that modify a variable in this dependency closure. And it suffices to only apply the operators that are applicable from this set. So let's have a look at an example again. So again, this truck example, where the two trucks have to drive from A0 to A2 and from B0 to B2. This can be formalized with two variables, T0 and T1, describing the current position of the truck, current location. And what we observe is that T0 and T1 are not connected in the potential dependency graph, which essentially means that the dependency closure, for example, in the initial state, only contains one of these variables. And again, it suffices to only apply, well, in this example, it suffices to only apply the drive operator from A0 to A1 and to prune the other operator. So in this example, the pruning power of strong stubborn sets and expansion core seems to be the same. And the question is, what about the general case? And well, this brings me actually to the main contribution of this work. What about the time? 5 minutes? Okay. Okay, so I'll try to hurry up a bit. Well, the main result says that strong stubborn sets strictly dominate actually the expansion core method in terms of pruning power. And to show this, we've shown this in 2 steps. So the first theorem says that, well, there exists an instantiation of the strong stubborn sets method. So there exists a methodology to compute disjunctive action landmarks and to compute necessary enabling sets, such that the selected operators by this instantiation of strong stubborn sets is actually always a subset of the selected operators by expansion core for all planning tasks for all reachable states. And I can't give the proof here for time reasons. A detailed proof is given in the paper. And this proof is constructive, so it's actually possible to implement it. The second step is an exponential separation between strong stubborn sets and expansion core. So there exists a family of planning tasks where the number of explored states with expansion core is actually exponential in the number of explored states with strong stubborn sets. So there are planning problems where we prune exponentially more states with strong stubborn sets than with expansion core. And again, I don't have time to go into more details here, but the concrete example where this occurs is also given in the paper. Okay, so much to the theory. Now we also implemented it and compared it in fast downward on the IPC problems, on all optimal IPC problems that are supported by LMCAT. And well, maybe I just switch to a summary of the results. So maybe we should have a look at the last line first. So these are the overall numbers of solved instances with A star, with expansion core and with the strong stubborn sets method, all with LMCAT. And well, what we observe is that, first of all, the pruning power of pure A star with LMCAT and with expansion core is roughly the same, 742 compared to 741. And what we also observe is that we got a pretty strong increase in coverage of 45 instances when applying strong stubborn sets. And yeah, so maybe we should have a look in more details at some problems. So these are all problems from the last IPC where the coverage of expansion core and strong stubborn sets differs. And well, what we observe is that in some cases, well, in extreme case, in the park printer domain and also in the woodworking domain, the effect of strong stubborn sets is pretty significant. So we overall generate less than 1% of the nodes generated by A star. In Scanalyzer, we do not get any pruning at all for both expansion core and strong stubborn sets. And in this case, because we currently pre-compute the interference relation of the operators prior to the search, we lose one instance in coverage because we just ran out of memory in this case. So overall, we got a node reduction with the strong stubborn sets in 26 domains out of 44, and coverage increase in 10 domains. Maybe very short look at the runtimes in more details. So in these domains, OpenStax and Park Printer, well, maybe I just skip this for time reasons. We got 1 order of magnitude in speed up in OpenStax, several orders of magnitude in the Park Printer. In Scanalyzer, where we do not get pruning, the runtime, the search time is roughly the same. And again, in woodworking, we get, well, several orders sometimes of magnitude efficiency gain. Okay, so this brings me to the conclusions. What we did is, well, we obtained a better understanding of what's going on of these 2 techniques. We showed theoretically that strong stubborn sets admit strictly more pruning than expansion core. And while our theoretical results are also supported by empirical evaluation in the fast downward planner on IPC problems. And what we particularly observe is that strong stubborn sets seem to admit, seem to lead to a strong optimal planning algorithm in any case, so which is kind of interesting. Okay, so that's it. Thanks for your attention.